Hello everybody! In this video I'm gonna present the solutions for the last two problems of the round, problem G and problem H. And as you may have seen in my previous two videos about this round, I got a really good result here. So I am using this as an opportunity to showcase my skills and also my explanation skills as I present these videos in a timely manner so that everyone can see the solutions after the round. So in this problem we are given a grid and we now want to find the GCD of the integers along the path from the top left to bottom right and the maximum GCD. For this problem there are two ways of getting it done. The first way would be to try some sort of a brute force. You get every value from 1 to 10 to the 6th and you try to see if we can have a path where everything is a multiple of that value. But this won't work because the constraints are far too big and we are constrained by the fact that we will need to try 10 to the 6 times. And you can even try some sort of a DP, but the issue with the DP is that if you keep some sort of a maximum, then you might discard your some solutions and it's quite hard to think at a DP for this problem. But we can observe something really important. Every single path from top left to bottom right will have two common values, and these are actually the top left and the bottom right values, and we can start by computing their GCD. And what this will help us here is that it narrows down the number of solutions we need to check to just the divisors of the GCD, because the GCD can only be a divisor of the GCD of the two values. And after we narrow the search down to this GCD, all we have to do is just to try for each divisor whether we can get from top left to bottom right. And this is something we will do very easily using a traversal from top left to bottom right and just checking a bunch of visited stuff. So as you can see here, I narrowed down the search to the divisors to the GCD of the top left and bottom right corner, and I just find the divisors. And I try it with J and with divisor GCD over J, and every time I just start from top left and I just modify the visited values if I have a valid path. So I do this once for J and one more time for divisor over J. And the reason why this works is that up to 1 million, the number with the highest divisor count has about 200 divisors. It's a concept called highly composite numbers. And the total complexity will be something like 2 times 10 to the 5 times this 200. So this solution will work very well and it will be well under the time limit. So once again, a problem where we combine math with some clever observations. Now, the next problem, problem H, is a really difficult problem, I would say. And I will explain roughly the ideas and also my explanation for why they work. I'm about 95% that what I did is correct, but just in case I get hacked, I have this disclaimer that I still had a few doubts when I made this video, but I'm quite confident that what I did is correct because it was also clean. So here in this problem, we have, imagine these tower defense games you might have played many years ago, and we have enemies which traverse along a path, and we want to get from top left square to the bottom right square, but it will go in a predefined path, and we also have a bunch of towers we can use. And now we can increase the range of a bunch of towers such that the highest amount of hit points the enemies start with is gonna be maximum. And also every time we upgrade a tower, the range also increases. Not the range increases, but also the hit points of the enemy. Like if we increase a range by 3, the enemy will have a hit point higher by 27. 3 at 3 is 27. And here there are, I would say, two key observations here. First, the grid is quite small, so you can do quite a few things without having to run into like time trouble or anything of sorts. And also, if we increase the range by too much, 3 at that power will go up like crazy. It will increase very fast, and for this reason we will limit our increases of ranges down to around 12. The limit might be slightly smaller, but I went with 12 for safety. And what signal us this really small limit is that we can actually do some sort of a bitmask DP. So the reason for that is that we can have this bitmask DP where we have a DP of mask, which tells us whether we visited this kind of configuration or not, and also the maximum initial hit points. And in order to do this bitmask DP, what I did was I pre-computed for every tower the benefit I would get by upgrading it by each range. The ranges are up to 12, so I just did every upgrade. And for this reason, I just pre-computed every upgrade and then I ran the DP. So I will show you more details on the implementation. So as you can see here, it should be loading in a second. Sorry about the interruption. I just put a defining long. I'm not a fan of defining long, but for this problem I wanted to avoid any issues. I pre-computed the square root because of the formula in the statement and also the powers of 3. And here I pre-computed for every possible range the gain I would get. Like if the distance is too big, then I don't care. And also I start with the gain being equal to -3 at that power. And then here for each tower I just run the bitmask DP and see if we can actually get something better or not. And then from that point I just went with all of the DP values, and that was pretty much it. Again, this is not a very detailed explanation, but it goes into the main observations and also the way to implement this by pre-computing and then using bitmask DP. So if you enjoyed watching this video, please subscribe to the channel and make sure to also check out my previous videos where I covered the previous problems, and also my video from yesterday where I talked about my 5-year anniversary. So thanks for watching and see you next time. Cheers!